It's AR, INT, the first one.
Okay.
Okay, so thank you everyone for being here, and thanks to the organizers for having me. So I'll be talking about Lorentz invariance and QCD equation of motion relations for generalized Proton distributions and generalized transverse momentum distributions, and the impact that these have on our understanding of orbital angular momentum and the proton spin. This is work that I basically did during my thesis and with my advisors Minetta, Michael Engelhardt, and Aurora, and it's based on these two papers. Okay, so the main motivation for this work is the spin crisis. We don't understand how the spin of the proton is distributed amongst its constituents. Then what I've been studying is the orbital angular momentum, how it is defined using generalized transverse momentum distributions, and well, these two theoretical objects, the GTMDs and the GPDs. We worked out a connection between the two definitions, and the kind of relation is known as a Lorentz invariance relation. And you can derive more relations using the equation of motion and look at Manzura-Wheelcheck relations for twisty objects. Okay. So we understand that the quark spin contribution to the proton spin is small. It's 30%. So we need to look at other sources, and one of the sources is Platonic orbital angular momentum. So how do we get to it? We start with the QCD Lagrangian, and from there you go to the energy momentum tensor, which gives you a way to define the momentum, angular momentum, and other properties of the proton. And basically these objects are also related to moments of generalized Proton distributions. So that's where the observables come in. So it's very basic, but basically if you're looking at a process with which can be factorized into a hard part and a soft part, the soft part is basically you parameterize it in terms of unknown functions. So for something like deep inelastic scattering, you would get PDFs, which describe a correlator with two quark fields, a projection operator in the middle, and so we're looking at the cross section, so you have the same proton state on both sides. And it's a forward process, so it's, I mean, the momentum here are identical. So GPDs are entering an exclusive process. So, I mean, they describe the soft part of an exclusive process. So it's the same photon, which is highly virtual, so that you can still talk about partons, and so that you can look at the quarks, and then it radiates a real photon. So you have two probes here. One is the Q square, which is very high and is giving you access to the quark. And the other is the fact that your proton remains intact at the end of the process. And the momentum transfer here is important. It gives you access to where the partons are located inside the proton. So now the soft part, it's the same, it's almost the same correlator that occurred previously, but the momentum is different. I mean, the proton state here is different from the initial proton state. So GPDs basically describe the amplitude. They're not describing the cross section. And because you have another degree of freedom in terms of delta, you have more functions. So at leading twist, you have H and E that describe this correlator. So as I said previously, you can Fourier transform in terms of this momentum transfer delta and get access to the spatial position as well as the longitudinal momentum fraction. Okay, so why are we studying these? Is like one of the main motivations was that starting from the energy momentum tensor, and so this is the quark momentum distribution, and so this looks like a cross product, and this gives you the definition of angular momentum of the quarks and gluons, and and putting in the QCD Lagrangian and working it out, you have the quark spin and the orbital angular momentum, whereas the gluon part in this formalism you cannot separate it into the two, but and working through it, you find that this is actually the quark part is related to the x moment of the two GPDs, H and E. And this was G's sum rule in this very famous paper. The important thing to notice here is that this is the total angular momentum. How do we get to, and the spin was already measured before in previous experiments, just with the forward, in the forward limit, and I mean in the forward deep elastic processes. So the orbital angular momentum is basically the difference of the total that you probe with these functions and the spin that you had earlier. So in this pioneering work by Polyakov and also Yoshitaka, there's this relation that we have this, which is the total J, the total angular momentum, and you take the difference between the total and the spin. Not that you take the difference, but you find that there is a distribution function, which the x moment of which gives exactly this form. So you have something on the left-hand side which connects directly to OAM, not, I mean, there is a function here, there's an x-dependent function here. Now, I want to add just one thing, that there is like a change, and not a change, but there was a new paper by Meister-Metz and Schlegel in 2009, which parameterized all the twist 2, twist 3, twist 4 GPDs and GTMDs, and they adopted a different naming convention. So I'm going to stick to the more recent one, and basically this G2 here corresponds to E2 T tilde plus H plus E. So you see this E2 T tilde a lot, and whatever relations I show for this guy basically connect to the fact that there was this work already. So anyway, so yeah, that's just an aside. But it's important because both these are used and then it's confusing. So I'm going to stick with this one. Okay, so we've talked about the x-dependent quantities, but in processes like semi-inclusive deep inelastic scattering and many other things, you get access to not just the intrinsic, not just the forward momentum fraction, but also the intrinsic transverse momentum, KT. You don't keep the proton intact in this situation, you just detect one of the many possible things. So let's think of a situation in which you combine the GPD situation and the intrinsic transverse momentum. So you have both access to both the position, whereas as well as the intrinsic transverse momentum and the forward momentum fraction. And I mean, in principle, these processes, you can imagine why they're hard, because we were connecting something when the proton splits and like disintegrates to the quark momentum inside. But for a GPD, you need the proton to remain intact. So yeah, they're difficult to measure, but there's a lot of work in that direction. But anyway, so when we look at a case when we have all these degrees of freedom, we have more functions, and we can now think about orbital angular momentum as a cross product between position and momentum. And this GTMD right here actually connects to OAM. So if you think of a longitudinally polarized proton and unpolarized quarks inside, so this situation, so it gives a probability density sort of unpolarized quarks in a longitudinally polarized proton, and we weight it with the operator that we want to calculate. So this is the orbital angular momentum part of it. We find that the orbital angular momentum is basically this kT squared moment of that function. There is another GTMD which describes spin-orbit correlations, and there are similar formulae like kT squared moment of G11, which also is important. But the basic idea is this: that you weight your Fourier transform of the GTMD with this sort of with this function, and just integrate over the V space, and you get this form.
Can I ask a quick question?
Yes.
So this WXKTD.
Yes.
You say it's a GTMD. Where is the difference to Wigner function?
So this is the Wigner function.
Okay.
It's actually good. This is the GTMD, and you Fourier transform
from it, and I have the Wigner function. Okay. Perfect. Understood. Completely happy.
Okay. So. So we can think of, now we've sort of seen two approaches to defining orbital angular momentum. One is as this kT squared moment of this GTMD, and the other as a difference of the total angular momentum and the spin. Everything here is collinear. There was no kT entering this picture, whereas everything, well, not everything, but this one thing that enters is a kT dependent quantity. So is there a connection between the two approaches? Yes, and it's a form of a Lorentz invariance relation. So if we think of this, I mean, it's not an X moment or any, I mean, this integrand here, I mean, because, I mean, yeah, so this part here we can think of as a distribution of, like, without the integration in X, we can think of this as a distribution of orbital angular momentum in X. So, so this part here is giving you access to an X-dependent distribution of OAM. So I'm just going to denote this kT squared moment as F141. So there is an X-dependent distribution of orbital angular momentum, and it's connected to GPDs in this way. So I want to say that this has been derived for a straight gauge link, and I'm going to elaborate on that more. So how is this relation derived? So we've looked at this correlator before. There's the quark fields, and GPDs enter at this level, where there's only there's momentum transfer between the final and the initial proton, and there is the quark momentum fraction X. So that's the only intrinsic quark momentum that's entering the picture. We can go one step before, in which the correlator is described by the momentum transfer, but and also the intrinsic KT. And then we can go one step even before, in which you have all four directions of K included. So you haven't, I mean, nothing, neither of like the Z components of these quark fields is zero. And this Yeah. So we can, the same way that you can think of writing GPDs in terms of GTMDs, you can also think of writing the GTMDs in terms of the functions that parameterize this correlator. And you can think of the GPDs also being parameterized in terms of, written in terms of functions that parameterize this correlator. So I have, instead of a correlator, I'm going to just write W at different levels, and here I'm writing it. So the completely unintegrated level, where you have all four components of Z and K, you have these functions, I'll just call them the A's, that enter. You integrate over K minus and the number of functions reduces. You integrate further over KP and you get the GPDs, which are, yeah, they're fewer actually because they are different. These are different projects. So the projection operator also makes a difference.
So last week we heard from Leon that, for example, this integration over KT from a TMD to go to the normal collinear PDF is far from trivial to show this. And then he showed this, and as is it the same case here? Is it so obvious that if I integrate over KT, I really get a GPD?
Well, I'm working in that limit. I'm assuming that you go from just this, and when you integrate over KT, it's just a delta function in Z and ZT, and that's it. All it does is set ZT to 0. So whether it actually happens and what we measure experimentally, I'm not sure.
Yeah, but have you? So Leon actually really did the work and integrated it out for. So he took a TMD, did all the work calculation, and showed that indeed, if you integrate, you get for the quarks. For the gluons, it doesn't work because you have the two TMDs, say Weizsäcker Williams and the dipole, and if you integrate one over, you don't get at all the forward. But as a normal collinear,
it must be a model.
This the stuff that Leonard was talking. I don't know. I wasn't there, but I assume Leonard talks about is not what she's talking about. It's
I understand
Yeah.
this completely.
Okay.
I was asking whether this complication which is there from TMD to normal PDF is also here from
Yes.
a GTMD to a GPD, and whether you have shown that if I integrate, I really get this. That was my question. I just used it as an analogy.
It's more of a starting point for me.
Okay, that's totally fine. I just wanted to understand. I just made this analogy to understand whether this complication is there as well.
In fact, that's a great question because that complication is there, but for us, it's
You have assumed it works.
Yes.
Yes.
Which is perfectly fine. I just wanted to
Well, we will
understand.
see.
Yeah.
So
Yeah,
We haven't assumed that either.
I have one thing. So the integration of a KP is technically not 0. It's technically not defined because that is subjected to normalization. So in some sense, we don't need to sort of think that if we integrate things equals to 0. It's just that there are some caveats related with the normalization that one needs to, in principle, treat correctly to be able to reproduce the platonic picture that we want. And so so in the work that I was with Len, we just basically say, okay, what is required in order to achieve that? So something like that has to also happen here.
That's what I was asking. That is exactly what I was asking. Whether it's the same thing works.
And I'm
That's all I-
satisfied with this rendition. Okay,
Thank you.
Sorry, can I ask a much more simple question? So if you have K minus dependence in your starting, well, at the very top coordinator,
Yes.
and then you parameterize it in terms of some coefficients.
Yes.
So how does it come in?
How does it come in?
Yeah, so K plus dependence gives X, K verb remains
I
K
don't
verb.
know what.
Those coefficients you have on the next slide, they are explicitly dependent on K minus, right?
Yeah, but yes.
Or I mean, it's dimensional also.
Okay, so I
want to.
It
There's Lorentz
basically-
invariant, right? So that
it's dot products. I mean, it's of course 4 vector products of K and P and K and delta. It's but that's okay.
Okay, so you could just, if you take the forward chain to simplicity,
Yeah. So it's just K dot
just
P.
have,
K dot P and K squared. Those are the two invariants.
right, so you think that the P is, so it's K squared, so virtuality.
So yeah. So yes, we have these functions, and we can write the GTMDs and the GPDs in terms of these A's. And what's interesting is that there are some GPDs that occur with an explicit KT, and which are relevant because, as we saw before, the orbital angular momentum has this KT squared moment. So it's exact, and that happens because you already have a KT sitting there in your parameterization. Okay, so just a small aside. This is a non-local operator, so the gauge length is very important. And so if we connect the two the quark fields that we have by just a straight line and not worrying about a staple, then at this level where when there is no integration over K minus, this has no idea what the light cone is. There is no way for this thing to know what is the z direction. So the only momentum degrees of freedom that enter are delta and K and P. Whereas if you have a staple link, it's connected, you go to light cone infinity, and then you have a transverse displacement, and then you come back. So there is, even though there is, you've not integrated over K minus, there is an extra vector n. And because simply because you have this additional degree of freedom, you have many more functions parameterizing the same thing. So in the straight line case, there are far fewer functions. And at the heart of it, that's why we have Lorentz invariance relations, because the A's repeat themselves and you're able to connect functions to one another. If you use the staple link instead, the relation I showed earlier, there's another Lorentz invariance relation violating term that pops up. Okay. So because you don't have any information about the light cone at the completely unintegrated level, the same A's describe F14 and E2T tilde. So E2T tilde parameterizes the gamma perk operator. So what I'm trying to say is here, if I use not gamma plus, okay, here, this gamma is the same as this gamma. So if I use gamma plus, it's the same A's. If I use gamma perk, like if I use a gamma perk projection here, it's the same A's. But for the GPDs, that's not the case. If you use gamma plus, you get H plus E. If you use gamma perk, you get a different function. But the A's remain the same. And when you write out your when you write out your function in terms of the A's using the invariant products that you have, you see this, that the derivative of this function in X is related to the GPDs. So on the left-hand side, you have the KT squared moment of a twist 2 object, and on the right-hand side, you have a twist 3 object. So, okay, this is sort of like an aside, but the same way that your completely unintegrated correlator has no information about the light cone, we can think of like completely integrating the quark degree of freedom out. So when you look at the form factors, and when you think about when you integrate the GPDs, you will integrate them to the same form factors, whether it's twist 2 or twist 3. So it's the same idea. Okay, so I'll go through this really quickly, but basically, as I said earlier, in the case of GPDs, if you have a gamma plus projection operator, you have twist, or even the GTMDs, it's twist 2, whereas if you have something like gamma perp, it's twist 3. What that means is that you're including a bad component in your description, like an operator like gamma perp, and a bad component is basically a composite of a quark and a gluon field. So at twist 2, you have this interpretation in terms of number densities. At twist 3, it is problematic. You can't really do that. So at the heart of it, you're connecting something which has intrinsic transverse momentum, and on the right side, you're connecting something which has quark-gluon interactions. And that's what these relations are. So I showed you for one of the cases, for F14, how this is done, and you can also, so this is the case of longitudinal spin. You can also do it like an unpolarized quark in a longitudinal proton. You can also do it with the quarks polarized, and you can also do it for transverse spin. Okay, so and now so you can also, okay, what this is the Lorentz invariance part of it. I have not used the equation of motion here at any step. And so now I'm going to go to the equation of motion, but there's just one thing that I want to say, which is that when we describe this kind of an object with proton states and quark fields in the middle, we can think of this. So these are the two proton states, and this is the struck port, B in, and when it comes back, it's the B out. And we can, so there are two sort of independent positions, the in and the out. So we can think of two linear combinations. One is the difference, like how much it has moved, and one is the average. So the momenta that we measure, the momentum transfer and this x, are actually conjugate to, so delta is conjugate to B, and K is conjugate to Z. So K is conjugate to how much the quark moved, and B is, delta, which is the momentum transfer here, is conjugate to where the photons are located. Okay, so why did I go into all that? Because the way the equation of motion relations are derived are just using this. I mean, this we all know. That's just basic stuff. And what you do is you stick an operator in front of the equation, and you put in a gauge link, and you complete the correlator. So I'm missing the slashes here, but basically this part of it is just there, and I'm multiplying by a psi bar and putting in the proton states and adding the Fourier transform parts of it. So, and we know that this should be 0 because it's all just starting from this thing here. And these derivatives act on the quark fields, but because of the addition and subtraction, basically what it ends up doing is bringing down factors of K or delta. And what's important is that if you need to really pay attention to the gauge link and the gluon field, because that's what gives you the genuine twist-3 aspects. That's what gives you the quark, explicit quark-gluon quark contributions. So this is after you calculate and you so this is a correlator. After you get rid of the derivatives, you just end up with correlators which you can parameterize in front of the functions, and this is a form of the equation of motion relation. And these deltas and kp's come because of those derivatives. And here is the genuine twist-3 term. So, and this is what it looks like. So now we have a relation in which there is the GPD and the GTMD that's occurring. So we have two independent relations. One was the Lorentz invariant relation, and the other is this equation of motion relation, and we can use it to eliminate the KT dependence, which is what I'm saying here, and that's what gives you the Vanzura-Wilczek relations. So this is the Vanzura-Wilczek relation. We've gotten rid of F on 4, and what that's done is allowed us to write the twist3 vector GPD in terms of twist2 GPDs and a genuine twist3 term. So this, sorry, the genuine twist3 is something that contains the explicit mode field. Any questions? Have I just lost my audience here?
Can you go back a couple slides?
Yeah.
On one. Yeah. So, what determines your choice of operator?
Okay, that's a very good question, because yes, so this, okay, so this is I mean, we want to connect vector GPDs with I mean, we want to understand, okay, I don't have the, I can, so these are all chiral even things. So this is a vector twist3 GPD, this is axial vector twist2, but everything's chiral even. So if you put in something like not sigma I plus gamma 5, but I mean, this allows you to basically write all your twist3 GPDs, vector and axial vector, in terms of twist2 things. But if you wanted to look at chiral odd twist3 things, twist3 GPDs, you would change this to gamma plus or gamma plus gamma 5. So because this contracts with the gamma vectors in this derivative and decides what it is that finally will be expanded.
And like I said, this is completely analogous to the work that has been done from TMDs. So all we did is just
Take it off forward.
the GTMDs,
Yeah.
and consider the so-called UL and ALU configurations that were forbidden by parity
In the forward.
in the forward case.
Yeah.
That's all.
Yeah, so this is the same operator you would use if you did a little g2, which is the yeah. So this is the approach is exactly the same as what is done for twist3 PDF. Okay, and then we can take moments. Once we have it in a form such as this, we can take moments of the twist3 function, and so because you see here that there's h plus e and h tilde occurring in this form, you see explicitly that this is g's. Okay, maybe there's a minus sign of, or not, no. Like you add h plus e on both sides. So e2 d tilde plus h plus e gives you exactly the difference of j minus sigma, as in the g pictures. That's why this x moment gives you OAM. And when you go to the x squared moment, you actually see the quark, explicit quark on quark term come in. And you can do this for the other spin configurations. What's interesting is that the quark mass only occurs for some of these, but it only occurs for the axial vector, just 3 GPDs. Yeah, this is the transverse spin case. So this is the last part of what I plan to talk about. But as I said earlier, everything that we that was shown was when we connected the two points by a straight line. If we were instead to use a staple cage link, we would have another term that would essentially break this Lorentz invariance relation, and it's called the LIR violating term. And as we saw earlier, when we go to the staple, the number of A's increases, and we can write this term in terms of the A's that occur. And it is essentially, so we can look at this object in the straight line case and the staple case. So little a is basically the difference of the two situations. So, so basically, it's the torque term, because you're looking at orbital angular momentum in the staple case and taking the difference with the straight case. And we can do the same study for the Sivers function and get access to what this quark-gluon-quark correlator is. Yes. And there's actually a work, so it's the derivative along the V minus direction, which is the staple direction, and of this correlator. And there has been work on this on the, I mean, you can do it on the lattice, because you have, that is one case where you have the functions as a, like you can write your GTMD or whatever you want as a function of the staple length. So taking a derivative with respect to the staple length gives you access to some of these moments. And for the case of orbital angular momentum, you don't take derivatives, but this thing is non-zero at for a straight link, and taking a difference of a straight link with the staple gives you the torque term. Okay, so in conclusion, we basically looked at a different way, yet another way of deriving Vanzura-Wilczek relations for TRIS-3 GPDs, and that allows us to study the X dependence of these quantities. These GPDs are associated with, things that you connected to GTMDs. So this gives you a way to look at things that the GTMDs were describing by measuring the associated GPD. And finally, the term which was denoted by calligraphic M, which is the quark-gluon-quark interaction, that's at the heart of TRIS-3 effects and should be studied.
Questions, comments?
Have a genuine naive question. So for the generalized GMDs that has KT dependence, as you very clearly said, Proton doesn't break up, there is no ions, etc. So how do you probe that KT? So how is it experimentally one can access that KT?
Okay, that's not my work, but there's work by Yoshitaka and also by Andreas Metz and Bhattacharya. But from what I understand,
Is that the discussion?
Yeah.
Yeah,
That's also psi.
relative momentum is the probe of the KT.
yeah.
So there is a general, so we've been working on this too. We haven't put out a paper yet because I wasn't sure. The issues always use operations with factorization seemingly. And so did Andreas, I guess. Andreas assumes factorization. So anyway,
No, it's only one group.
it's only one group.
One group.
One loop. Oh yeah. Okay. Yes. All right. So exactly. So the main issue there, to answer your question, for GTMDs, you want to see a GTMD. Was that your question? In the sense that was not your question.
No, that is his question.
How to measure GTMDs?
Well, naively, so so the KT has to be on a finite scale, so something has to be sensitive to the KT, right? But then I was naively thinking, well, but the proton doesn't break up at the end. How do I see a KT? So it has to be some very specialized object that I get.
So this is it. Okay, so that's a different question.
Oh, is it?
How
Okay.
to measure. So how to measure GTMDs? The comment. Okay, can I have one comment is that you need two planes. You can no longer have just there's a lepton plane and a hadronic plane, and on the hadronic plane you produce whatever. Here you need one plane for the KT and one plane for the delta T, and these two planes have to be listed. So that's why Yoshi or Max at the double gradient, because one gradient is not enough. There's only one plane, so you need two planes. That's a difficult. But this was not the question.
Yeah, no, but even with the two digits, I think it's a bit.
This is a moment. It enters like exactly like think about F1 fever. Think about the KT square moment of F1 fever, which she had there at some point in the site because we have the generalized version of that too.
Yeah.
So it's the same physics that we're looking at.
This thing we're talking about corresponds to story about sediment.
Yes.
And that's the regulations which also sheet distribution of apartments inside the relation between water motion and steam. So now what is the way how to access that particular? So I'm talking about Proton.
Yeah.
So you have to extract the function to be some independent. You have to take a certain moment of this function. You cut it out. Well, now people have said for many years how do you take a moment of the function which is not defined in all regions. Because this particular function is all divided into all PT. Okay? But maybe what we actually showed after the first group, this integral actually exists first of all, and it corresponds directly to the future of logic element that we have to use principles of representation. So it answers this question.
What do you think?
I mean, I think Nobu is saying that in series you break up the proton and you take just a part of it which you connect to the KT of the quark. Whereas in a GTMD you need your proton to remain intact. So where is the KT probe?
Yeah, that is a very naive question.
And
like very simple.
I'm not the best person to answer it because I'm not worked on it, but I understand that it's not easy, but you can do it with the way Yoshitaka or others have said that.
But it works with that transformation, even if the protons break proton. So
Yeah. So it's the same physics.
how to access it? It's a different thing. You have to have some probe that will test.
So the imbalance of digests is sensitive to KT, whether you go into the exclusive region, which Yoshi needs for his Wigner function, or whether you just measure TMDs. So that is kind of because if you don't have any KT, your digests are perfectly back to back. And as soon as you have intrinsic KT, you get an imbalance of the two digests. And that is true in a normal TMD version, and it's true in the exclusive one, which Yoshi had. So you measure the imbalance between two objects which are basically should be back to back, and the imbalance of this is your KT. So that has been shown also in the low X kind of limit where they want to measure this linear polarized fluons and so on. There's all this other work by Adrian, Jamal, and so on, where always they use digests to measure the imbalance of the KT. So basically, so that has been shown by, I don't know, there's by now something 10, 15 papers to do that, and that's also what Andreas does he just uses this psi x c, and I don't know what the other particle was, which was in his paper. So he also measures this invariance.
Other questions, comments?
Did you figure what's that?
Yeah, so I just wanted to clarify, because we heard many things, just to see how the things connect, that the G orbital angular momentum is related to F14 with a straight gauge link. It's true only if you integrate over all the momentum variables.
Brilliant.
Okay, so as Yoshi has shown, and also shown in other papers, that there is no unambiguous definition of, there's no way to define a proper definition of G's orbital angular momentum as a density in X. Does that
You
make
can
sense?
always add something that integrates to 0.
Yeah, just that.
The operator level doesn't work because G's orbital angular momentum is the full covariant derivative.
no
And these do
operator.
not commute, so you cannot define an eigenstate of the momentum. So there's no density in this sense. You can only do that with derivative that commute, so that's the pure gauge covariant derivative. And if you take a straight
But
gauge
it's a
link,
matter of definition.
no.
If you can define F141 in
No,
a straight
G-
gauge link and connect it to
G
orbital
defines
angular
as the
momentum,
total covariant derivative.
no, that's fine. But if you look at F141 as an object,
Yes.
which has this transverse
Yes, you can
ZP.
define an orbital
So
angular
if you
momentum as a
connect
function
that
of
to
X.
orbital angular momentum, then
Yes.
why not?
That's another. It's a function that depends on X. It has the meaning of orbital angular momentum. It's not the G. It's what is called a function
Yeah,
here.
I mean-
It's a canonical one.
Yeah.
That's the one you connect to your distribution through the Lorentz invariance relation.
True.
And the relation with the G is only integrated. So you can define it, but never call it G orbital angular momentum. It's a
True
function of
that
X.
it's only when you take the X moment you see that
Yeah.
it satisfies
Just
the
to
G
make
sum
it
rule.
clear,
But it is a
it's a
density.
different. It's a density, but it's not the G density. It's
But
not
it
a
is,
density.
it is an orbital angular momentum. You can't deny that.
Yeah, but you can't say it's G
Okay,
angular
fine. I
momentum.
would say it's
No.
Your slide shows the connection with the M. That is the thing. Where you define the M at some point.
this.
No, well,
I mean,
do you have the summary with the? Is that the summary with the all the genuine thing? Yeah, yeah. That. So.
Of course, there's an add auto measure, just connects to different definition of English.
what?
Look at the first line where you have the x integral, right?
Yes.
Decay integral.
Yes.
What if I just do the decay integral?
Yes.
That function be a
That's the one
X
here.
dependent.
That's the one here. But that's, strictly speaking, it's not a kinetic orbital angular momentum. It's not something you can construct with a full covariant derivative. It's something that is defined as a non-local objects in the function gauge.
I just have to disagree. So
I just look at that function.
Yes.
Or that
Exactly.
function of
Yes.
x.
No, it's an orbital angular momentum, there's no question about it. But never call it G's angular momentum, because G's angular momentum is the one that is defined as a full covariant derivative, not the non-local object defined in the
But that's
General
after you
Integrate over TP.
This is some that's the momentum.
Yes.
Integrated, right?
So function per gauge is important because that's where the straight is.
Exactly.
I see.
So any density in X or K curve, actually you can also define an L of X and K curve, which I also mentioned in the paper. It's just B integral over B to integral over B to B, B cross
Yeah,
J curve.
one of the things I started with.
Yes. That works as well. You can also define phase space.
With
So
with
the-
a straight.
you can do it with a straight gauging or any gauging actually.
but I think that the question here is just like the physics is not pointed at clearly. So what we put the accent on, and it was on that connection with G2,
That's the point.
is this. Well,
That's what I stress. I'm not saying that you're wrong, not at all. I totally agree, that's correct, I've checked anything. But the thing is that just to make clear, because there may be conflicting information or misunderstandings, that some people would say that there's no X dependence we can define for the G angular momentum. Yoshi says, and I agree with him. And still, you can define an X dependent from the F14, but that's another orbital angular momentum.
Yeah. So sorry, I have been raised. Physics is an experimental science. Okay, so I try to always make connections of the things that we do with the observables. But that's what this paper is about. So, we made a connection. We spin a connection between G, orbital angular momentum, defined as G, with the covariant derivative, and the Jaffe, defined as a Jaffe. And the difference between the two, as pointed out by Yoshi and Burkhardt in different ways, and then yet again by Aston in another way, is given by, and she has it, right?
Yeah, it's this.
Yeah, it's that.
This guy.
Oh, that's what I wanted. Yeah.
So you have, so this is the one where we have no staple. It's just a straight connection with the distribution. And you have this one with the staple, and the difference is something that depends on a quark to on quark.
Which is, I think, the big expression there, which has two pieces.
Yeah.
One piece is from the gauge link. So it's a twist 3 piece, which is that complicated object in there.
Yes.
It's composed of 2 parts. One part is from the gauge link, and one part is the genuine quark. Okay.
I'm just saying, one has to be careful that there's no conflicting saying that there's no G-X dependence where there is, you can define an X dependence for the orbital angular momentum with F14 and straight.
So now you go out and do the experiment, okay? So when you go out and you do the experiment,
you can measure the functions, but if you want to call it orbital angular momentum, you have to massage and see what it is.
Ah.
I can. You will find also the literature if G is himself proposed to call LG of X actually the integral of H plus E. They give the same integral. They have 2 density.
it's wrong, right?
Well, the integral is correct. We have a function of X, and so people might define it as the G density in X.
But we're not people. I mean, so
Speak for yourself.
So last time I checked, I thought I was still not a kid.
I lost 98% of the work of the control. So for my self-education needs, can I write L Jaffe monocurrent is equal to the same formula as the first one, but the F14 will be with staple link?
Yeah, so
is that-
L Jaffe Manoir
so
is
that
the same expression.
Our is 1%.
I mean, I have it here. So it's basically the straight link case plus this.
Yeah,
This-
I'm not very familiar with the F14.
With a statement.
Okay.
I mean, F141.
And again, you do differential one.
And now L Jaffe monocurrent X.
Exactly. That one, as we have shown in the paper, you can define it as a function.
Yeah, F141 is basically the KT square movement.
So there is no problem.
Okay,
with
sorry, you
Jaffe
can do
Manoir.
this. You have no problem with the Jaffe Manoir. It's only the G, strictly speaking. And actually, you can generalize that any canonical one associated with a certain path, changing the path, just the path. But all of them are strictly speaking canonical as a function of X. Only one, when you integrate over X, happens to be equivalent to the G with a full covariant derivative. Yes.
So when you go back to experiment, so basically what you can measure, so you can measure the
But you
OAM
can-
part,
the
but
only
you cannot
thing-
measure the difference between Jaffe and G. Because it's given by, because of this complicated way that the twist tree, it's given by the twist tree.
Experimentally, hopefully that one, but very complicated. And these ones. So experimentally, we can access the stable if we can get the GTMD observables and the straight via the Lorentz invariance relation through the GPDs.
So yeah, so this, on this I agree. That's the only statement I agree.
That's fine.
On this I agree.
And that's basically the point I made.
Yeah,
was
that's
trying
what I'm
to
saying. But just, but
I think the only thing he is saying, if I interpret it as a translator, I think you all agree. The only thing he's saying is that Elke should never say that there's an X dependence of the GL.
right.
I think that is what he's basically telling Elke realize that you cannot measure an X dependent of the G orbital angular momentum.
No, Michael, and that is our co-author. Show the Michael.
Michael computes this, and this.
Michael computes the G X dependence. Can
No,
you
no,
just
he
show
finds this quantity.
It's all different. It's just called Schwingle.
It's a canonical one.
You cannot define
You can
indication of
string
G
process.
this length that you have.
So
I'm not
understand
sure,
you
I'm-
correct? That is what you were telling me, that I should never say this? Okay, I am happy to say this. I can.
Should
Okay,
we
then
continue
you
the
will disagree
discussion?
with Michael. That
Should we-
is- you
sorry.
know,
No. Okay, yeah,
Should we
Excellent.
continue?
No, Michael, if it's integrated over X, it's fine. And showing the integration over X, it is fine. As a density in X is not true. But integrated over X is perfectly fine. Because integrated over X, that's the G. So what I say, the G is the Foxfinger integrated over X.
I don't think Michael has a function of X. It just has total, just a
Yeah.
It doesn't
Yes,
count
yeah.
the components.
Yeah.
Right.
Exactly. So there's no problem with Mike, because you never looked at the differential in X.
I think you really
It's
agree.
fine. You're fine too. You just use a different thing.
I mean, I never
No.
said
But
the
it's
G
not
is
the
density. I mean, I said straight length, which gives you the.
G, but only integrated over X.
I
Yeah.
What's the
really,
density
I
in
really
X?
think he doesn't say that you said this. It was more really aimed
Exactly.
on Elke.
Okay.
So it was, I really, because I that's at least my understanding, and I don't think you said this. It was really kind of more that I don't get confused with all the operators.
Not against these two densities. It's okay. It's okay.
Exactly. There's no there's, at least I am, there's
You're
no,
gonna go out and, okay, maybe it's just that,
Maybe
maybe
it's
it's
just-
maybe it's just semantics here. We
exactly,
probably
I
agree.
think so.
Because we probably agree. Okay. But I have to think about it.
That is
Conceding
also,
that we agree, yeah, okay.
so I suggest we make 15 minutes coffee break and then we come back and discuss what we want to write down. Okay.
Good.